All right, hi, welcome back to AP Physics 1, Unit 4. Again, this is the WEP unit, Work, Energy, and Power. In this video, we're going to combine the last two videos into one simple theorem known as the work-energy theorem. So what we say is that the net amount of work done on an object will change the amount of kinetic energy the object has. This relationship is what we know as the work-energy theorem, okay? So this is a very important theorem, okay? So the way you think about it, I apply a force, I accelerate the object, which means I change the velocity of that object. And if I change the velocity of the object, I change the kinetic energy of the object. So that's how it all kind of works, kind of progresses. So mathematically, we say that the change in kinetic energy is equal to the work done on the object. Okay, now I'm going to go up here to the right-hand corner and kind of expand this equation a little bit more. In fact, this equation or this relationship is how we get one of the kinetic energy or the constant acceleration kinematics equations, right? And so that's how we get this v squared equals VO squared plus 2a delta x equation. This theorem is exactly where it comes from. So work, force times distance, and you can throw the cosine theta in there, is equal to 1/2 mass final speed squared minus 1/2 mass initial speed squared. Okay, now I'm not going to show you the derivation, but if you kind of go through and solve for v, right? If I go through and I solve for that final velocity, and guess what I get? That equation right there. Okay, so now we kind of redefine what work is. Before we just talked about how it was a force exerted on an object over a distance. Now we're going to look about this idea that work is actually the process by which a force transfers energy into or out of the system, right? So here's that idea that work is a transfer of energy, okay? In fact, if you look up the definitions, it'll say energy is the ability to do work, and work is the transfer of energy. So you can see it uses each other in the definition, right? And so if I do positive work on an object, my change in kinetic energy is positive. What does that mean? My speed increases, right? If I do negative work on an object, that means I have my change in kinetic energy is negative. What does that happen? What does that mean? My speed decreases, right? Think about what friction does. Friction is a common force that does negative work, and it slows down objects, okay? And if I do zero work, well, my change in kinetic energy is zero, which means I have a constant speed. Okay? Now, again, when we look at this, each force that performs work is the means by which energy transfer takes place. So regardless if it's friction or if it's, an applied force, regardless of that force will cause energy to be transferred. So if we look at the gentleman here with the car, he is applying a force, right, in a direction, which means if this car is initially at rest, he will accelerate the car, which means he changes the velocity of the car or the speed of the car, okay? So if he applies it for a distance, he is going from an initial velocity to a final velocity. Same thing with the horse and carriage, okay? So let's look at it. An example problem. So here the example problem says, suppose you push a 30 kilogram package with a constant force of 120 newtons through 0.80 meters. The opposing friction force averages 5 newtons. What is the net work on the object? What is the change in the package kinetic energy? And if the object starts from rest, what is the velocity after that 0.80 meters? Okay. So if we're looking for the net work, right? So again, let's do our free body diagram. Okay, so we want to find the net force acting on this object, right, to find the net work. These, again, normal force and weight don't matter, okay? And again, it's not really going to matter here because they actually tell us how much the friction force is. And so I've got 120 Newton force minus a 5 Newton friction force, and that's going to give me 115 Newtons. Okay? Now, what I'm going to do is I'm going to multiply that to find my work. So net work is going to be force times delta x, or distance, right, or d. And so it's going to be 115 times 0.80. And you'll have to excuse me, I forgot my calculator. Let me split the screen. All right, skip for now. I apologize for this. So 115 times 0.8. So it's going to be 92 joules. Okay. And right, there's going to be positive 92 joules because our friction doesn't completely take away our force there. Now, what is the change in the kinetic energy? Well, now we apply our work energy theorem, and that's going to be positive 92 joules, right? Oftentimes, if a question is set up like this, those two will be the same number. Okay, and now part C, we're going to find what is the speed of the object if it starts from rest. And so I'm going to say delta K is equal to 1/2 mv squared minus 1/2 mv initial squared. Well, v initial is 0, so it makes that whole term 0. And so all I'm going to do is I'm going to solve this for v. So v is going to be 2 delta K over m, and we're going to take the square root of that. So I'm going to do 2 times 92 divided by mass, which will be 30. Okay, so 2 times 92 divided by 30, oh, not 60, divided by 30. And then we're going to take the square root of that, second square root, second answer, and it's going to be 2.48. Okay, so the speed of the package after applying this force and experiencing that much friction will be 2.48 meters per second. Okay, so now here we go. So this is going to kind of finish up the work energy portion. Now we're going to start focusing on conservation of energy. We're going to talk about mechanical energy, potential energy, and then we're going to talk about bring it all together with conservation of energy. And then finally, we're going to talk about power, which actually is more suited to deal with work.